Okay. Hello, welcome everybody. My name is Marko A. I used to be a Ph.D. student with Francis Heligan 7 years ago. So it's 7 years since I last been in Brussels. And since then I've did a postdoc at Los Alamos in Center for Nonlinear Studies at Los Alamos National Lab in New Mexico. And after finishing up my postdoc, I had a short stint at AT&T working on network science and graph theory. And since then I've started my own company doing graph analytics. This talk is primarily around new software that I've been developing with my company to do graphs at scale. How do you compute on graphs when they no longer fit within the memory confines or the disk confines of a single machine? So this talk is very technical. It's hopefully we can please ask questions. I don't know everyone's limits of knowledge. I'm more than happy to entertain questions and go down particular paths. If I breeze over something, I make a lot of assumptions about people's knowledge of computer science and technology that exists out there currently. So with that, this talk is sponsored by Los Alamos. I gave this talk a week before now, a week ago, at the Big Dig group in Los Alamos National Lab. It's a big data group. There's a big trend in both business and some sense in academia to how do you deal with very large scale data sets. Distributed computing is becoming more in vogue. It's becoming easier to do distributed computing because of things like Amazon and EC2, which allow us to yield as many machines as we need. It's machines like a utility, much like using gas or electric is like a utility. And so a lot of organizations are now starting to think of how we can start to leverage distributed computing more efficiently. And there's a lot of platforms that have come out to allow it to be very easy to express distributed computations and to implement them cost effectively without having to buy all the hardware. And the work that I was doing with Los Alamos was this project Ecosystem, which is led by Herbert von de Sampel, actually of the University of Ghent, and now is at Los Alamos, and he's been there for the last, I don't know, 20 years or so. Just by happenstance, also a Belgian, which is always seems to come around. I'm always in, by the European connection is always a Belgian connection for some reason, given that it's a small country, I don't know why. And this system is, they're interested, Los Alamos National Laboratory has this problem in the sense that they have postdocs that come, and Los Alamos is in the middle of the desert in New Mexico. It's an isolated laboratory, and there's reasons for that due to the construction of the atomic bomb back in the World War II. But now it's kind of a hindrance because they bring students and they teach them, they do their postdocs, they do graduate work, and then they send them out into the world, and they never come back. No one ever comes back to New Mexico. It's a very isolated place. And so what they want to be able to do is track students as their careers evolve, knowing that there is some kind of affiliation, alumni relationship with these students. Tracking people is now is facilitated by things such as Twitter and Facebook and LinkedIn and SlideShare and GitHub and Archive and all these digital repositories where people are leaving artifacts, digital footprints about themselves. And so what we're able to do now is not only find students based on their name but also their discipline, and then start to figure out, okay, it's called the discovery process. This student has this Twitter account, and that Twitter account uses the same handle as this SlideShare account, and he talked about these concepts, and those concepts were also in this paper, and that's him in this paper, in this repository, so forth and so on. So we're building a big model of these students as they go about their lives and their careers, so that in the future the director of the lab or any kind of researcher in the lab can tap that network and utilize it for whatever purposes they want. And then ECCO, with the Global Brain Institute and Francis Helig and the work that they're doing helped to bring me out here and provide a talk. So, we call this a vertex. A vertex can have an ID, a long value. A vertex can also have properties. These are key value pairs. This vertex is a long ID 0. Its string name is Faunus, and its integer date born is 2012. There's such thing as an edge. An edge connects two vertices, and this other vertex has a vertex ID of 1 as well as key value pairs as properties. An edge can also have an ID. An edge can have a label. For example, Faunus depends on Hadoop. These are edge labels, multi-relational graphs. And an edge can have properties as well. So this is the data structure we're dealing with. It's called a multi-relational property graph. There's multiple ways in which things can be related, and those things themselves can have key value pairs to give extra metadata to the particular entity in question. And so we build up graph structures like this. Things relate to each other, and this is your classic graph representation. Well, let's go ahead and look at this particular vertex and its neighbors. So together, these are vertices and edges. We call them elements. And we have our vertex IDs, our edge IDs, our edge labels, and our element properties. What we're interested in doing is how do we represent this in memory and ultimately on disk. And one way in which to do this is the adjacency list representation, in which you have a vertex and all of its incident edges connected to it. For example, for vertex 1, we have this vertex on the left. 1 is its ID, its properties are EF. And then we have all of its incident edges related to it. For example, the edge going from vertex 2 to vertex 1 is ID 4. It has properties C and D. Its edge label is A, and the adjacent vertex of the incident edge is 2. So you just have this long list of concatenated elements like this. We also represent the incoming edges and the outgoing edges. We'll talk about why you have this double use of information. So this is an adjacency list. If you think of it like this, you have a bunch of vertices, 0 through 11, and with those vertices, the row columns maintain incident relationships. If you have a cluster of machines, for example, at these IP addresses, so you have an adjacency list in a cluster, you can partition that adjacency list such that it exists on multiple machines. Have anybody heard of Hadoop? Has anybody heard that word before? Hadoop. So this is becoming very popular in the lexicon of big data. Hadoop was Google found out that there was a pattern they kept repeating when they're analyzing large data sets. And it's called this MapReduce pattern. And MapReduce comes from functional programming, where you're going to apply a function to a whole bunch of data points in parallel. There's no communication between those functions. It's a map function that's just going to do something to that input and yield some output. The yielding of that output can be tagged such that outputs that have the same tag get grouped together. And that's called the reduce phase. And so that you can now join elements that get emitted from the map phase and then do one more type of computation off of that. And you can chain these MapReduce steps together. This became a very nice paradigm because it's very easy to implement in a distributed system. It's very easy for people to write code to do distributed computations. Hadoop is an open source version that was developed by the Apache Foundation, and it has 2 components. It has HDFS, which is a distributed file system that takes any single cluster of machines and makes all their file systems within a single address space. So this makes it so that you can write files to this file system, and if that file overflows the address space of one machine, it automatically gets written to the next machine, so forth and so on. So from the abstraction level, you're thinking of all these machines having one single disk. And what's nice about it, it has the same kind of flavor of a Linux file system, where you can remove files, add files, list files, create directories, do permissions, all these kind of things. It has that same kind of look and feel as a Linux system. That is the structuring mechanism. That is where you store information. And the next thing beyond storing in computer science, you can structure information and you can process information. And so with every kind of structure, you need some kind of a process, and the process by which Hadoop uses is something called MapReduce. MapReduce is that model where I described, where you have a bunch of map functions, and the joining of the outputs of those map functions is the reduce, and you're operating on key value pair data. So in essence, what Faunus does, it constrains the generality of Hadoop. Hadoop works with any arbitrary key value pair data, but the key value pair data we care about in Faunus is vertices and edges. So Faunus provides a way in which we can structure data graphs into this distributed file system. How do you represent these graphs on a distributed file system? And then how do you then go about doing some kind of processing or traversals on those graph structures? And you store the graphs using HDFS, and you process the graphs using MapReduce. So before talking about structuring of graphs, let's talk about how you process these graphs. And this perhaps is the most specific or give a nitty-gritty of how we move traversals around in this data structure. So assume a data structure like this, and this is back to the property graph we talked about in the beginning. And this is we call it the graph of the gods. It's our toy data set that gets distributed with all of our technology. It's 12 vertices, and these vertices represent, for example, we have Jupiter. He's a type of god. His father was Saturn, who was a type of Titan. Jupiter lives in the sky, and it's a type of location. He has his brothers Neptune and Pluto. Jupiter's son was Hercules, and Hercules is the demigod. A demigod is something that is both a god and a human, and his mother was human. She was Alcmene, so that's why Hercules is a demigod. Hercules, at one point in his life, created an egregious sin by slaughtering his wife and his many children. Due to a curse that was put onto him by, I forget the goddess's name, because he denied marrying her. She wanted him to marry her, and he said, no, I don't want to marry you. So she put a curse that made him crazy, to made him kill his children. And the king of the land had said, well, instead of punishing you, what we're going to do is make you go through 12 trials to regain your respect. And so he did 12 trials, and we have 3 of these trials here that he did. And we see that he battled the Nemean monster, the Hydra monster, and the Cerberus monster. What is interesting is in this kind of graph representation, you can also, of course, put metadata on the edges. This is something you don't see in textbooks, but something you see in practice. So if you study graph theory from the perspective of academia, you see single relational graphs. These are vertices and their edges, and there's no label between them. The most advanced kind of semantics you'll get is directedness. There is a relationship that's not necessarily symmetric. When you go into using graphs in practice for modeling worlds, you want to say, well, there's actually different types of vertices, and there's different types of way these vertices can interrelate to each other. They're not homogeneous. If you're looking at, for example, citation networks, those can be all homogeneous, because you'll say that there's papers, and papers cite each other. So I don't need to label the edges. It's all citations and directed citations. And you say, well, I'm going to look at now friendship networks. Well, everything is people, and people have friendships, and friendships, would say, are bidirectional, so it's unlabeled. If you now want to get into a system where you want to model people, papers, institutions, concepts, and the way they relate, for example, I have a friend, my friend wrote this paper, that paper cites this paper, that paper is published in this journal is maintained by this university, this journal has these concepts relate to each other in some way, you get into this multi-relational graph kind of structure. Things like RDF have become very popular in terms of modeling. Has people heard of RDF as a framework for modeling multi-relational graphs? This one of the drawbacks of the RDF model is, and we'll talk about it a little bit later, but is this notion of putting metadata on edges. And many times you'll say, for example, someone wrote this paper, but on the edge you might want to have, or someone liked this product, but on the edge you also want to say how many stars did it get in its liking. So when you start to model real-world systems or systems that organizations want to use for end users or for more complex representations, this kind of representation, this type of data structure becomes convenient, so to speak. So in Faunus, you have this data structure, and you have your cluster. I can log into the REPL. There's a graph traversal language called Gremlin. It's supported by most graph vendors out there. It's a functional language. We'll look at its components, but for now, just assume you jump into this REPL. A REPL is repeat, evaluate, something in loop. It's like the terminal for the language. I can look at HDFS. I can say, what files do I have in this using a simple ls command. There's no files in my distributed cluster right here. I can go ahead and copy from my local directory. I can copy the graph of the gods, and I can put it in there. So now I've copied this representation, and I put it in this adjacency list form in the cluster. Of course, you don't need 3 machines to represent 12 vertices, but we'll just assume that for the sake of... And now if I do an ls on the distributed file system, I see that the file does exist, its size, and who the permissions, and who the owner of the file was. So now I want to operate on this representation in the file system, and I'm going to go ahead and create a variable called g, which denotes my graph. And I have this properties file that provides a whole bunch of information about how I want that graph to look, and here are some of these properties right here. We'll go through each of them. The input format is this GraphSon input format. We'll talk about input formats in the second half of the talk. This is just a way to represent graphs using JSON. It's a type. It's like an XML. It's a modern XML. The graph output format is I'm going to do some transformations to this graph, these traversals on the graph. Where do I want the graph representation to ultimately look like? I'm just going to put it right back in JSON. Where do I want the output of my computation to go? I'm going to make a directory called output. And if that directory really exists, should I override it? Yes. And if I have a side effect in my computation, if the computation is not yielding a mutation in the graph, but some kind of data structure like a statistic, that statistic is not in graph form, it's not contained within the graph, it's a side effect of the computation. Where do I put what output format do I use? And I'll just use a text file output format, which is like a tab delimited format. And so let's go ahead and do an operation. If I do G.V, what I'm ultimately doing is I'm saying I'm going to put a gremlin on every vertex in that graph, capital V meaning all the vertices in the graph. And so at this point I have my adjacency list of representation, and I have a little one saying that there's one gremlin at every vertex in this graph. This compiles down to a single MapReduce job. If you are familiar with Hadoop MapReduce, you can chain these MapReduce jobs as long as the output of the reduce is the same as the input of the next map. And ultimately that's what we're going to go ahead and do. The next thing I can say is, well, I want to do a filter on this such that I only care about those vertices whose type is God. And at that point, most of the gremlins in the graph die, and there's only gremlins at particular vertices in the graph whose type property is of type God. And then I can say, well, I want to know of those graphs, of those gods, who are their children. So who did they father? And so I can take an incoming step walk of father that's going to go ahead from Jupiter to Hercules. Neptune and Pluto had no children, therefore those tokens die. And at this point, I have one walker on vertex number 7. And then I can say who is the mother of that father, of that child, and that gets me to alchemy and give me her name, and at the bottom of my output's alchemy. And this compiles down to 3 MapReduce jobs. So while I was discussing the fact that we represent a vertex in its adjacency list, or its incident list in this manner, one thing that we're also doing in this representation is that the only thing we have is the graph. The graph is the data structure we're operating on, so we need to store all traversal information within the graph structure itself. So you have to think of the vertices and the edges also maintaining a representation of the traversers. And there's 2 ways to represent a traversal. One is cheap, and it's just a counter-based mechanism. How many traversers are at this particular vertex? And that's just a long value I can increment or decrement as things move in the graph. Another thing, and it's more expensive, is an enumerative model in which I list all the traversers. And the reason why I would list all the traversers is if the traverser's history is pertinent to its current state in the computation, then I need to enumerate them because I cannot compress them down to a single long value. I need to have a list of traversers, and each traverser might have other information about itself that allows me to do some kind of a larger computation. And the perfect example of this is if I want to know the path that I took through the graph as I solve that path equation. So if I have, give me all the vertices, put a traverser at every vertex, filter those that such type as God, give me their father, give me their mother, and tell me the path I took. Well, we see that Faunus will tell you that path calculations are enabled. The problem with path calculations, while they allow you to keep this historic information, which is necessary for detecting cycles, necessary for doing backstepping to go to a previous step I'd previously been at, there's a lot of things you can't express with a regular grammar, which is if you didn't have this kind of history information, this ultimately comes down to a push-down automata. If you do not have that kind of historic information, ability to save information about state from previous, then you couldn't enumerate, for example, the path that you took. However, this means that while you're also propagating the gremlins, you're also propagating all the state information. And when we're talking about graphs at scale, and we're talking about doing computations that start at all vertices and emanate in every direction, you're talking combinatorial explosion, because the path branching factor, depending on your paths. So it's while state information is convenient and very nice, some computations you just don't want to do it because it becomes very expensive. To the point, actually, do I have? Oh, I don't have that on me. There's a computation we did. We wanted to figure out how many 5-step paths were in DBpedia. So DBpedia is a graph representation of Wikipedia, and that is if you enumerate paths, that becomes excessive. If you do a counting mechanism where you're not enumerating paths, but you're actually just aggregating counters, the number we came up with, I think it was like 500 quadrillion. Do you remember that? No, it's not even more than, what's one more than quadrillion? And we were able to calculate that in 40 minutes because of just the counter versus enumeration. So the ability to just aggregate based on counter versus aggregating based on enumeration, you don't have that kind of computational explosion. So certain computations, you say, wow, how many 5 steps, including cyclic, not just simple paths, exist in a DBpedia graph, which has 250 million edges. Just the mathematics or the explosion of the amount of passes is massive, and it is massive, but it's computable if you choose the right representation. Yeah, I forget the number. It was one more than quadrillion. I forget. It was a number I never see. I never heard the word before. I was like, yeah. But it was impressive in that sense. I was like, yeah. So Gremlin, and so you express these computations, and I assume if you come from a in the world, there's like this world in academia of graph. They don't really think of graph processing as graph theory, and you're proving theorems on graphs and the structure of graphs. And if you go into practice, you think of a graph as like a data structure that you're trying to query. Is anyone in a relational databases? So relational databases, you have tables, right? And these tables, you do joins on tables based on some predicate to say how 2 tables are going to intersect. A relational database is like a bunch of Excel spreadsheets. And so the language you use in which to intersect these tables in order to get new tables, it's a closure over tables in essence, is SQL. In the graph world, you query the graph data structure just like you query another database, but you query it using a traversal. How do I walk this linked list representation? How do I move along this graph in order to solve what we call path expressions? And a path expression is composed in Gremlin of these functions. And these functions take some type of an input and yield some type of an output. And you got to make sure that the output of one is the same as the input of the other, and you can chain them together through function composition. And this provides the semantics of your traversal. There's 4 types of traversal categories or function categories. One is a transform. A transform in its simplest form is you're going to have, I want to go from a vertex to another vertex, so if I'm going to do a walk from a vertex to its adjacent vertex, that's a transformation from this vertex to that vertex. Or if I want to get the name of a vertex, that's a transformation from the vertex to the string representation of its name. So it's a transformation of input to output. You're mapping, and when you do traversals, it's a power set, because you're ultimately saying from this vertex to some set of other vertices. You can represent a set of other vertices. So if I have the outgoing, if all of you are my friends, and I get to me and I want to do an outgoing step, then I'm going to have to walk to all of you. And so I go from one vertex to a set of vertices. That's the transformation. If you do set operations, that's more of a breadth first representation. I go from this to everybody, versus a stream-based representation, which is depth first. I go to Pierre, then I go to Clement, then I go to Eva, so forth and so on, and I have a stream representation. So when you think of Gremlin, you have to also think about the operations of the sets you're manipulating. Are you manipulating sets that'll be depth first, or breadth first? Are you manipulating streams that'll be depth first? A filter takes an object and either yields that object or does not yield that object. For example, a filter is something of has age greater than 30. So if I'm at a vertex, I have a whole bunch of traversals at vertices, and I do a filter of has age greater than 30, those vertices that do not have age greater of 30 just are not admitted. So it's a filtering. A side effect, and most people in functional program hate side effects because they're not clean in the sense of compilation or provability. But what's nice about side effects is that you can yield statistics about your graph as you're traversing it. And so a side effect will take an object, a vertex or an edge, and yield the vertex or an edge, but in the process produces some kind of output. And things like this, you see in this in like relational databases, group counting. Give me all the names of the universities or the
all the types of institutions I'm at, or it could be a business, a university, a high school, and give me the distribution of how many are there. There's 500 universities, 1,000 businesses, so forth and so on. Other kinds of side effects is a manipulation to the graph. For example, I want to traverse relationships of father-father to produce grandfather. So taking a step from one person to his father and to his father's father yields me a step of my grandfather, and then I can do a side effect that mutates the graph by adding that. It's a derivation. And branching we won't get into, but branching is a way to express regular languages in the sense you can get recursion going. So let's look at some typical examples of traversals. How many people attend each academy? So academy in the Roman would be like a university of today. So I have a whole bunch of, I have a graph, and I put vertices, or I put traversers on every vertex in the graph, and then I filter out all those traversers that are not of type person. So now, that are of type person, so I have all the peoples, and then I take an outgoing walk to the things that those people attended, and then I filter out all those things that are not academies. I get the name of those academies and I group count. So if more students attend one particular academy, there's going to be more traversers at that particular academy. And so when I do a group count on its name, then I'm going to have more traversers at that particular thing. So I get a distribution of the people at every university. The next one is an interesting use case in the sense that because the graph is the only data structure that we can actually manipulate through our computation, you can yield side effects, but you can't use those side effects back into the computation. If I wanted to get the degree distribution of a graph, so degree distribution is the definition, is defined as the amount of incoming or outgoing edges for a particular vertex, and natural graphs have very nice properties that make it different from random graphs, and people study the degree distribution. Are people familiar with networks and graphs and power laws and random graphs? And or I'm talking, would you like to hear? You understand? Okay, so what is the structure of a graph? People would say there's, well, if when I look at a network, I would say that there's vertices and they're just randomly wired together. If I randomly wire together vertices, the degree distribution falls a Gaussian. So in that sense, most vertices always have about, I'm going to make up a number, 50 to 20, 70 edges, and everyone's pretty much the same. Look at Twitter. On Twitter, is everyone the same? No, there's the Britney Spearses of the world, there's the Barack Obamas, there's the popular people, and then most of us are just the plebeians. So there's very few people in the world that are very popular or very rich, and most people are not very popular and not very rich. Yeah. So that kind of distribution you get also in most natural graphs. Think of your vein structures. Your jugular, how much blood flows through your jugular versus how much blood are going through all the little tiny veins that go and feed all the other cells. So you get this kind of more flow on very few veins and a lot of flow on very many veins, or very little flow on very many veins. And this structure is over and over again. We see this in airports. How more planes, there's so many San Francisco airports, but there's a lot of little regional airports. So Frankfurt's a very big airport, but there's not so many Frankfurt airports out there in the world. So most airports, if you look at how they do their air flight lines, you'll see a bunch of hubs and then a bunch of little regional jets that fly to little tiny towns. So that kind of structure is very good for routing information. If I need to route a bunch of people from one side of the world to the other side of the world, I'm going to find a hub, get them across, and then do another little hop to another regional, and then do a bus, and then do a car, and then walk. So you get this kind of this pattern of less efficiency, but you want to get the main veins to do the most work. The problem with that is to random disturbances, that doesn't destroy the flow of information or the flow of transportation. If I was to roll a dice and say which airport is going to be destroyed, the probability is I'm going to hit one of these little regional airports. There's a lot more regional airports than there are the Frankfurts and the SFOs of the world. However, if I'm intelligent and I want to do an attack, I would say, well, I'm just going to take out San Francisco, and that would greatly destroy the flow of information. So these kind of power law graphs, or these graphs that have these kind of skewed distributions, are very susceptible to intelligent attacks and very non-susceptible to random attacks in terms of how they process or function in terms of the job they're trying to do. So a lot of times what you want to do, the first thing you do when you get a graph data set is you say, I want to get the degree distribution. It's the first computation you want to run because you want to know if it has this kind of quality where there's very few vertices that have a lot of edges and most vertices have very few edges. And so how would you express this? And you express it like this. Let's go ahead and get a graph. We'll call it G. And we're going to put a gremlin on every vertex again, the same pattern we keep doing over and over. And then we're going to do a side effect. And this side effect is we're going to set this property on the vertex, because remember, vertices can maintain properties. We're going to create this property called degree. And that property is going to be equal to the count of its incoming friend edges. So every vertex is going to count how many incoming links it has to it and set its degree property to have that number. And then we emit the degree property for all those vertices in group count. So if a lot of vertices had 0 incoming edges, then they're going to have 0 and it's going to have a big number, 1, so forth and so on, to all the way to 1,000,000, which might have 1 or 2 vertices that have that number. So this is how you do degree distribution. How many 3-step acyclic paths exist in the graph?
Excuse me.
Yes?
Is this kept, this property, this agreement?
Yes, it's a mutation of the graph and now it exists. Yeah. You could do another side effect after you've done the group count just to drop it. This is, and I apologize because I'm coming from the world of, I assume a lot of people have been working with graph technology, and this is a kind of problem with this talk in the sense I come to a group of people who might not necessarily have been working with graph databases for a long time, and so if I give this talk to people who have been working with graph databases, then it's unique in the sense that that the only computational structure you have is the graph, and so if you're not in the MapReduce world, all you have is that one data structure, so all you can do is mutate that one data structure through these steps. And so that's why you have to leverage the data structure if you're going to save information through to its future state. If you're doing something with a graph database, you can have external data structures where as you're traversing, you can look up, mutate, and keep going and do something else. In MapReduce, you don't get that flexibility. And so this is how you trick this computational paradigm to support that kind of representation. Acyclic paths, this is going to be very expensive because now when I get to this simple path, I can just go to every vertex, take an outgoing step, an outgoing step, an outgoing step. When I go to simple path, what I'm telling the compiler is like, oh, I can't tell if this is a simple path. A simple path is a path that hasn't cycled. That means every element that I've touched is unique. So in order for me to when I get to this filter, this simple path filter, I have to know if every element I've touched is unique. That means that filter has to know what these previous elements were. And that's when you enable path calculations. So now the gremlins are no longer just one counters, because if you have a long ID for a long value for a counter, that doesn't maintain the history of the traversal. So now I have to enumerate all these paths, and when all those paths come through, I have to look at those paths and do a hash on the path to see if the path set reduced in size. If it didn't reduce in size, then I know it's unique. If it reduced in size, then I know it's not unique and there's duplicates in it, and then I filter out the traversal. I say, oh, this is a duplicating path, you're dead gremlin. And only the gremlins that don't have replicating non-unique histories are kept. And then I count how many gremlins there are after I've done that filtering step. So this is the way of saying how many 3-step acyclic paths there are. Simple one. Put a whole bunch of counters on every vertex. Put one counter on every vertex and count how many counters you have. And then here's one that mutates the graph using a side effect as well. If I have a bunch of vertices, and this is also going to use path information, I have this graph, and I'm going to put traversers at every vertex in the graph, and I'm going to label that step X. Think of this like in the prologue sense, where I'm going to do like the question mark X and say this is a variable, and I'm going to bind this step to that X variable. And then I'm going to take an outgoing step from those vertices to the fathers of those vertices. And then I'm going to do that again to their fathers, walk again. And now I want to make a link type called grandfather from where I am to the vertice that I saw at step X. So if I have a single path, and I went Marco to Jose to Antonio, that's my father, and now this gremlin is right here at Antonio, I referenced Marco back at X, so then it makes a link back to X, which is the Marco vertex. So Marco's grandfather is Antonio. What this does, and this gets to the difference between when you're doing this in bulk across all vertices versus before if you're doing it to one vertex, is that this is all happening in parallel. all the grandfather edges are being derived in a single step of the computation. The parallelism is, of course, defined by how many threads you have per machine and whatnot, but theoretically, you're deriving all grandfather relationships at one moment in time. So this gets into we're going to look at specifically how some of these steps are implemented. This gets into the flow of how data is manipulated as it moves through this chain of operations. So you have some graph, and as you do an operation on that graph, it mutates the graph a little bit because you're moving traversers around. And then I take another outgoing step and I move traversers around again, and then I do some kind of a count. The count didn't mutate the graph, this is the same color, but what happens is the count is yielding some kind of a side effect. So if you look at the file system, we have these operations being happening. If you look at the file system, I have user, Ubuntu, and then I have the output directory that we cared about. There's three MapReduce jobs happened. The first one, gv out, and count. So job 0, job 1, and job 2. And in any one of these folders, these are each individual folders, in any one of these folders, you have the graph that exists with all the traversers at that particular step, as well as any side effect that you produce during that computation, for example, the count. So this is how the directory structure works as you're migrating these graph representations through these job chains. You're creating an output, and then you're creating these folders for every type of job. And if you look at how MapReduce does its computations, it cares about key and value. You're going to do operations on keys and values to yield more keys and more values. In Faunus, we make a restriction such that all we care about are vertices. And so we don't care about the key. The key gives us no information, so it's null. And a vertex, as we saw in the beginning, is its ID, its properties, and all of its incident edges, incoming and outgoing, and their properties. And so when you have map-only steps, you're producing a stream of vertices and yielding a stream of vertices. When you're doing a reduce step, and why a reduce step matters, we'll talk next about how you implement a traversal, is that you go from a stream of vertices, and then you output these tagged elements. And let's hold off on this folder, but I'm providing a tag such that reduce is going to unite all those tags into one bundle. So I went from a long writable to a holder to a long writable and an iterable of holders, such that I've aggregated a whole bunch of things under that one long value, and then I can do a computation on that to ultimately get me back to my null Faunus vertex stream. So I'm always just keeping this stream of Faunus vertices, and that's the representation of the graph moving through this data flow. But let's look at how this would look in a computation, or how you do these kind of things. So MapReduce. Let's do a very simple one, is a filter. And a filter says either kill the gremlin or let the gremlin live. And let's go ahead and make our computation, this top left, this thing that's tilted sideways. It says g.v has type God. All vertices such that their type is God. And we don't care about the key, it's null. And we care about this vertex, which is the current vertex we're processing. In parallel, all vertices are being processed in parallel. In theory, it depends, of course, how many threads you have, what the parallelism, level of parallelism is. But just think about all vertices in parallel being processed. And we have this thing called the context, which is this machine, the Hadoop machine, where you can give it information. And so what do we care about? We care about the key and the value we're going to be processing. The key is the type, and the value is God. So from the context, we get some user-provided key, the user-provided type, and the user-provided God. So we get the provided value and the provided key. Now we have these two objects, key, value. And then I say, if the vertex does not have type God, then clear all the paths, kill all the gremlins that are currently at that vertex, and then write the vertex to the stream. So I never delete a vertex, I'm not deleting vertices, I'm killing off traversers that are at those vertices. Because again, as I'm going through my steps of computation, the graph, I need the graph. So I can't, if I destroy the graph at one point and I go to the next step, I might need those vertices again. So I'm propagating the graph through, but I'm mutating the traversers that are on that graph. And so a filtering is not destroying the vertices, it's just destroying the traversers that are at that particular vertex, and then I write the vertex back into the stream. Most map-only steps are these kind of predicate-based operations. Given some filter clause, either kill the gremlin or not kill the gremlin. So I take a whole bunch of vertices with the gremlins on them, pass them through a filter, and some of them die, some of them survive. This is probably the more interesting of the operations, and this is how you do a traversal. A traversal in MapReduce lingo is called a reduce side join. So a join operation is where you have two independent data structures, and I need to figure out some predicate by which I can say that this data structure intersects with this data structure. And so if I'm doing a traversal where my vertices have pointers to other vertices via long values, I need to be able to take that vertex structure and all those references and join that structure with itself such that now I can make a walk from these vertices to the next vertices, and then join that structure with itself from those vertices to the next vertices. So a join is a way to do like in graph processing, you're joining the table with itself. And let's see how that would look. We're going to do a G capital V out. I'm going to give traversers to every vertex, and then I'm going to take a one-step walk out. I don't care about the key, it's null. I care about the vertex, and I care about the context. For all the outgoing edges of the vertex, write to the stream the ID of the adjacent vertex. So if 1 has a link to 2, write to the stream the number 2, where that's the key, and the value is the paths, the vertex itself, but only its paths, and I'm going to tag that P. We'll see why that's important, and I'll keep going over this because this is an important part. And then once for that particular vertex, once I've emitted all those things for all of its outgoing edges, I write the vertex itself and I tag it V. Now at the reduce step, let me see if I can walk over there. Hold on. A little tangled. Okay, now at the reduce step, I've been getting all these long values. Here's a long, here's a long. And so now I have the long, and I have all the things that were put into that long tag. So now I have all the paths of the vertices, and I have the vertex itself. So what I'm going to do is I'm going to create a new vertex, and this vertex is going to be that long ID. And that vertex has nothing, it's just a vertex with a long ID. But now I need to reassemble that vertex based upon the stream of incoming tags. For all the holders of that tag, if the tag is V, that's the vertex I wrote out, then add all the information about that vertex, its incoming edges, its outgoing edges, its properties. I've reconstituted the vertex. If it's not V, then it must be P, and then add the paths that you've seen to that vertex. So now that's the path information of the gremlin jumping. Now the path information, which was on this vertex, is now on this vertex. Because at this point, the path information was on this vertex, but I'm sending it to the ID of the adjacent vertex. So the V reconstitutes the structure of the graph, the P reconstitutes the paths. So now I've migrated all the traversers to the other vertices that are adjacent to it. And in this essence, and because it doesn't matter, because it's a distributed adjacency list, and Hadoop will maintain all the IP addresses and it doesn't matter for me, I just know that I'm reconstituting the vertex and migrating potentially between machines the traversers where they are in the cluster of machines. Kind of get it? The important part, and this is in any time you're doing anything with Hadoop, and the important part is you have one stream. So if it's like you have like so much bandwidth, and if you're gonna have multiple information channels, then you need to make sure you tag your channels. It's like doing modulation in a signal. So the modulation we're doing in the signals, I need to break this stream into two streams. One stream is the graph itself, and the other stream is this propagation of traversers. And then I need to reconstitute that stream back to just being vertices. Because I need to work at the vertex level, but at some point I need to move a whole bunch of information. So the reduce step allows me to break the computation into two streams, the graph and the paths, and then reunite such that I get back just to the graph. And that breaking apart and migrating information is the distributed traversal. And then the final one is a side effect. Here's a typical side effect you'll do is where you'll have For example, for every vertex in the graph, what is the distribution of types? For example, how many gods are there? How many humans are there? How many demigods? How many monsters, given our running example? This is interesting in the sense that we have 2 contexts we're going to write. The context we've been working with this whole time is graph as the default. And if I want to write to another file, I need to define another context, and we have this thing called SideEffect. What I'm going to get is the type. So this is the user provided key, which is for type, and that's going to give me, for example, the value of that key. I'm sorry. Give me the user provided key, and so the key is type. And then I'm just going to write the graph out to the stream. I don't do anything to it. I just write the vertex. However, I'm going to do I'm going to have this other stream. I'm calling it a SideEffect, and the other stream is just going to go to another part of the disk. And I get the property, the type of that vertex, and I get the path count. For example, it's only been 1 because we only have one vertex one counter at every vertex. And then the reduce step is only on this SideEffect stream because we're not going to do a reduce on this graph stream. What's nice about this is I've outputted monster and I've outputted, let's say, 1. Another guy had outputted monster and outputted 1. Another guy had outputted human and outputted 1. At the reduce step, I'm just summing how many counters I have for that particular object. So this will be monster 3, human 1, so forth and so on. So that's how I do a degree distribution or any kind of a distribution where I need to aggregate a whole bunch of values and then figure out how many of those values exist. So graphically, you have a graph of traversals. They go through the computation, through the function, but you have some other kind of data structure that gets emitted as a side effect. Okay, so that's how you do filtering, side effects, transformations, which are like traversals, in this paradigm of MapReduce. What's nice about MapReduce, and I should get more into that, is because if you look at a lot of organizations now, organizations look for solutions. They don't look for interesting things. They don't care about what's interesting. They care about what's going to solve their problem. And the relational database for a long time has been the solution for a lot of things. People say, I start a company, I buy an Oracle license, and I'm using Oracle, and all my data goes in Oracle. I'm going to do some joins. I'm going to build an application that my front-end users can use, or admins can insert data. And even every university has their whatever system, whether it be Lotus Notes, or it be MySQL, or it be PHP, and they have the tools and whatever they do to maintain the information of their organization. We're starting to realize that if you're starting to aggregate more and more data, for example, how Twitter, all the amount of data that Twitter's aggregating or the amount of data that Google's aggregating, these common tools that people have been using all this time start to break down. Doing a relational database join on 1 trillion edges, on a 1 trillion row table, just doesn't work. The indices are too large, you have hot indices, there's just a lot of problems with doing large computations with relational databases. So people have to come up with new models of processing information. And what is nice about Hadoop and MapReduce is that it's become kind of like a de facto a way for every organization to say, if we have a lot of data we need to process in parallel, we have the machines, I just need an easy way in which to compute in parallel, then they say, well, that's what a Hadoop cluster is. So a lot of organizations just have whole teams that just maintain Hadoop clusters. Just like you had your DBAs who maintain your Oracle clusters. And so this kind of evolution of the processing technology we're using in organizations is what we're seeing. And so when you go to an organization and you can say, well, they say, we have a lot of graph data and we need to process this graph data. And you say, well, do you guys have a Hadoop cluster? Yeah. Well, we have a Hadoop framework that'll give you able to process your graphs on your Hadoop framework. It's a lot easier to say that than to say, here's some software that works at the disk level. You're going to have to train new people on how to maintain the cluster. You're going to have to train new people on how to program to this thing. You're going to have to, so you have to be very smart when you do something in business. If you're trying to propagate a piece, not even in business, if you're trying to make sure that people adopt a technology, you have to ride on substrates that they're comfortable with. If I came to somebody and said, I have this piece of technology, and they say, okay, great, what language is it written in? It's written in a language I made up. Okay, does it work for what machine? Oh, it's for this piece of hardware that I've designed myself. Okay, that's a very hard sell. So it's figuring out where in the abstraction level you want to get such that you don't compromise performance, and there is a lot of compromising in performance in this kind of MapReduce model in terms of how you do processing here. So it's like you want to not compromise performance, but at the expense of making sure that people adopt things and dealing with the performance hits later. So with this, let's go ahead and go talk about structuring the graph. So we've talked about how you process the graph, you move traversals to the graph given this function composition, and the next thing we want to talk about is how that graph is actually put onto disk. And there's different formats for representing a graph on disk. One is the sequence file input format, and this is Hadoop's just standard binary format. And you think of this as a list of serialized vertex objects in a binary form. So we had this stream of null Faunus vertex, and how you represent that on disk is how we initially showed, where we have the vertex, its properties, and its incident edges and its incident edges. You can do various tricks in compression. For example, if I can group all the edges that are friendship edges by a friend, and then I can have all the edges without repeating the word friend, and it's like a prefix encoding, and then I can have works for and all the works for edges, so I don't have to do friend, works for, friend, works for, friend, works for, so I don't have to repeat that string over and over and over. There's delta compression that works that we don't use in Faunus yet, but it's the idea of you have 64 bits for a long representation of a vertex, and if that vertex is making reference to a vertex that's that was created in relatively the same time as it, then the long value is probably not that large. So instead of representing 64 bits and 64 bits for the adjacent, I can write 64 bits and then the delta. How much offset do I get so that I can squeeze a couple more bits out of my representation. What other kind of compression scheme? Variable width. Oh, variable width encoding is a nice one. Variable width encoding is the idea of, actually I don't know how variable width works, but the idea is this, is you have a long value and you have 64 bits for a long value. And so what I can say, let's say 8 bytes. So I have 8 bytes for a long value, and I can say, well, I'm going to make a long 9 bytes. However, that's at the max. If I do the max value of a long, it'll be 9 bytes. But if it's less, then I don't need to represent. Let me see how to explain this. If I have the number 256, I don't need 64 bits to represent 256. So I can represent that within a smaller, within three, or how many bits is 256? To the 7 bits. So 2 bytes, I can represent 2 bytes to represent the 256, and then have like a cutoff point that says if I see this bit sequence, then I'm done representing it, so the rest of the information is no longer that long. However, if I need all 64 bits, then I get my 8-bit boundary, then I'm going to need to use a 9-bit, the 9th byte to represent that cutoff point. So if you have a lot of large longs, you're gonna run into problems. But if a lot of your longs are in the shorter range, then you can save a lot on compression. At the end, it's the same size whether you use variable width or not variable width if you represent the whole address space. But most of the times you're not representing all the longs. 2 to the 64 is a very large number, so you can do this variable width encoding. Are people familiar with JSON? XML? Never heard of XML? Okay, XML. So XML is kind of is becoming outdated in its life. It's a hierarchical type of data format, text-based data format. JSON is also hierarchical in the sense that you represent key value pairs, and then a value of one of those keys can be yet another chain of key value pairs, so forth in an embedded fashion. So it's just like this tree structure you can build. It has a simple parsing to it, and people like it because it's easy to create, easy to parse, and you can represent nice structures with it. For example, if we want to represent a vertex, we have a vertex represents this whole row right here, and this is just an adjacency list. We have the key value pairs, name Saturn, type Titan, its ID, and then an array list of incoming edges. Father to vertex 12, of ID 12 to vertex number 1. So we represent this, and this is one JSON document. And we call this graphson, and it's a way to represent this graph in JSON. This is a nice slide in the sense that RDF. So RDF has been popularized by the semantic web movement and the linked data movement. RDF has some problems. The way you represent RDF is you have a URI. A URI is some kind of protocol and some namespace. http://twitter.com is a URI. It's an infinite address space in the sense that I can give any arbitrary URI to any object. And because the string can grow infinitely, therefore you have an infinite address space. And they said, well, this is very nice. I can go ahead and create a graph of URIs. And because URIs are in a distributed address space and you maintain ownership of your namespace, for example, twitter.com is owned by Twitter, google.com is owned by Google, markorodriguez.com is owned by myself, then I can have a graph of URIs that link people's individual namespaces and to make references to each other. And so what they say is, well, why don't we go ahead and make a graph data structure that's in an infinite address space, already has namespaces that individuals maintain themselves, and allow people to link their data into a global network of references between data points. And so this has, oh, that sounds very pretty. And we can go ahead and do that. And they say, okay, well, what we do is we have this thing. For those who do not know web style, you would do like, this would be HTTP : / Marko, and you just do an EX for like a name prefix. It makes it simple so you don't have to type all these things out. So EX Marko is actually some longer URL, HTTP : / So then I would say, I have this thing called Marko, it's this URI, and I'm gonna link it to a URI that's represented of a number. So there's a URI out there, and it's it exists only when you reference it. It's called 33. If anything is 33, it gets referenced to that 33 vertex. It's a URI that represents 33 as an integer and exists in this ephemeral space of all possible URIs. The problem with this is that when you represent this computationally, you represent this on disk or you're doing some kind of computation with it, that 33 becomes a supernode. How many things have 33 associated with them? So Marko's 33, the length of something in centimeters is 33, the height, how many objects does this thing have is 33, so forth and so on. So then you have a vertex that has all these incoming edges to it that represent that 33. What's nice about the property graph model is that what you're doing is you're saying, well, this is not something I care about graphing. I don't care about linking to the concept of 33. I don't need to make a platonic representation of 33. I can repeat instances of that 33 because it's just a data. It's not a vertex. I can just represent that as a data type. So with the property graph data model, you represent the age as 33, and then the URI is as Marko, and then you have a vertex. So when you map between RDF and the representation of a property graph, you're doing this kind of a transformation where you're taking things that are literals and putting them onto properties and keeping the URI which unites them as a property on that particular vertex. What's interesting too is that RDF is an edgeless representation. If you look at any representation of RDF, it's this. Most of them are these. N triple format, where you have URI, URI, URI in a big list, subject, predicate, object. Marko is a human. Humans are bad. Bad is a concept. Concepts relate to other concepts. And you just have this list of statements in this kind of semantic network. And that's the representation of edge list. It's a simple MapReduce job to take an edge list and join on the reduce for the particular vertex, and you have all the edges for which in the edge list associated with the particular vertex to make it an adjacency list. So it's a MapReduce step to go from edge list to an adjacency list, and that's how we keep that adjacency representation. So if you're going to input an RDF graph into Faunus, there's a pre-done reduce step, MapReduce step that turns the edge list into an adjacency list. I'll skip this. Should I skip this? Let me get to something. This is a cool factoid. So there's a paper, and it's free. I recommend anybody to read it. It's really simple to read, and it's very nice. It's called The Pathologies of Big Data, Communications of the ACM. This plot is cool in the sense of this. This is random access to disk, sequential access to disk, random access to a SSD, solid state drive, sequential access to an SSD, random access to memory, and sequential access to memory. That's the y-axis. The x-axis is the amount of throughput, how much bandwidth, how much data can I pull off this thing in a read fashion. Random access to disk is very slow. A disk spins. It's a mechanical device. And so if I have a very defragged data structure That means if I'm here and I need to get the rest of my data structure and the disk has to spin and then spin and spin and spin and spin and spin so I can reconstruct my data structure in memory, it's a lot of mechanical movements. And it's very poor, if you have a random access to disk, it's poor performance. However, if you're doing sequential access to disk, you're faster than random access to memory. So if my data structure is not defragged, so it's a serial data structure, as that disk is spinning, I'm just pulling data off that disk. It's a lot faster than the cache misses I'm going to do when I do to random access to memory. And this is why things like Hadoop are very nice, is because they write these serial lists of data structures, and what you're doing is you're reading up that data structure, doing something, writing it back down, the next step, reading it back up, writing it back down. You're able to take advantage of the memory hierarchy in the sense that you don't have to hold everything in memory. You're going to be bound by memory ultimately, so we're ultimately going to have to hit the disk. If I'm going to hit the disk, what's the best way to hit the disk? Make sure I'm doing sequential accesses to disk. So it's trying to optimize to make sure your data structures are laid serial on disk so you don't have that random spinning. And this gets into the difference between global versus local analysis. And this talk was assumed, unfortunately, assumed a lot of knowledge about graph databases. So when you think of Faunus, what it's doing is it just has these key value pairs in this serial fashion. And there's no indices. You have to do everything in parallel, in bulk, on all vertices of the graph. There's no index structures into this that I can hop arbitrarily into the graph. When you think of something like Titan, and I apologize, Titan, please look it up, titan.thinkaurelius.com. It's a distributed graph database where you represent, like a database, give me this vertex and walk out from that vertex and do some kind of operations. It's an index structure. You have your adjacency list represented like this, but then I can jump to an arbitrary vertex in the graph because I have an index on the keys, and then within the vertex itself, I have indexes on the edges, so I can jump to the father's edges, or the mother's edges, or the nose edges. So you have a lot of indexes. And when you talk about the difference, when you talk about a database, you're going to get defragmentation, and it's because you're reading and writing and deleting. And when you read, write, and delete, your data is going to start getting all over the disk. If you guys had Windows machines back in the day, they had this defrag. You guys remember defragging? And what that tries to do is organize your files such that they're as much sequenced on disk. In databases, it's called compaction. If you keep reading and writing, you're gonna frag out your data structures. So you compact them again, and you have these background threads that do compaction. That's going to happen in a read-write scenario. In a read-only scenario, when you have a single user doing some kind of analytics, reading up a graph, moving traversers, and doing some kind of like SideEffect computation, the data that I'm writing is already sequential, and I'm not mutating that data. It's not a bunch of people arbitrarily mutating that data. So I can take advantage of the fact that it's already sequentially organized for me on disk. And that's one of the nice things about Hadoop. It's not a database. It's a way of streaming data off a disk efficiently, doing operations. As that stream's happening, you're doing some operations on that stream and writing that data right back to disk in a stream fashion. There's no intermediate manipulation in that sense. While a database, in the classic sense, doesn't have that luxury.
Do you mean that you're just adding data, you're not writing any data all places that were already filled? You're just adding at the end?
Yeah, as you're creating copies of the data, and ultimately you're creating copies of that graph. As you're streaming in vertices, you're manipulating that vertex and writing that vertex back out to disk, next vertex, back out to disk, next vertex. So at some point I have two representations of that graph, and they're both sequentially organized. Of course, the smart thing to do is as you're reading up this one, you're deleting data so that you don't duplicate. But that's the principle is that it's not the same graph structure that you're rewriting to. It's a stream of the graph structure, and then you stream out to another area of disk. In a database, you don't have that luxury. It's the same data structure, and you're mutating the same object, doing some operation to it, and it's changing it on disk right where it was. And so if you only had a certain boundary on disk to represent, let's say the properties, name, Francis, age, something, a gender, male, and then I say, okay, and I bounded that, and he was in this area of memory, and I've been writing other vertices, and they took off from here and went this way, and some other area right here. And then I want to add a property that he has gray hair. Well, my bounds have already been taken over, so now I have to have a pointer some other area on disk to put the gray hair. And then when I compact, it's going to pull the gray hair here and push this guy over, and that's where the fragmenting happens. As I start to add more edges to Francis, I've run out of places because I hit a boundary, so I need to go somewhere else and write the rest of those edges or those properties. And so you really want to keep Francis co-located in disk, because I get those, ultimately, I get these kind of speeds. If I'm just reading the Francis vertex and him and all of his incident edges are all right next to each other, it's a fast read versus having to jump around. So a little side into Titan. We're really excited about Titan. There's a blog post called Educating the Planet with Pearson. Pearson is one of our clients. Pearson Education is provides textbooks to basically all universities in the world. A very large UK company. They are everywhere. You probably don't know it, but in some way right now you're giving money to Pearson. They're one of those organizations that don't make you don't know they exist, but they do. It's like Cerberus. There's a great company called Cerberus. They purchase organizations, and you've never heard of Cerberus, but the fellow who owns the aggregation of all these companies, from car companies to whatever, he's filthy rich because of his ability to stay hidden. What we've done with Pearson is they came to us with the problem. They said, there's this movement in online, it's called MOOCs, massively online courses. They're saying, why do we have universities? Why do we have these physical buildings? These things do not scale. If a teacher teaches, he only teaches to 20, 30 students maybe. He can't get that kind of outreach. He can only do so many students per time. There's only so many lecture halls. There's only so many students we can actually have. We only have so many dorms that the students can live in. So there's like some scaling issues to a university. If a university wants to get bigger, it has to buy more land, hire more professors, make bigger rooms. And I say, well, that seems like an imposed scaling factor to education. It's not necessarily a necessary aspect of the inability for a university to scale. So they say, well, Pearson right now supplies books to universities. How can we take the middleman out of it? How can we just teach the students themselves, and we don't need this infrastructure of universities? So they say, well, how can we go about doing that such that we can, in essence, provide education to anyone on the planet? They came to us and said, can Titan scale to educate the planet? And what does that mean? I want to represent 7 billion people, all reading books, in discussions, attending courses having concepts relating to other concepts, this concept talking about this discussion, Marko mentioned that, Marko has mentioned this, has expertise in this, so forth and so on, this kind of education graph of books and students and teachers and concepts and discussion boards and groups and study groups, these kind of notions. And so they said, if we're going to go down the road of using Titan as our database to represent that kind of a online environment of people sharing information, and we need to see that it can scale. So what we did is we used, oh man, I wish I had, let me see. Do I have it here? No, I don't. I don't have internet. And so what we wanted to go about doing, and it was a great opportunity for us because we can put a lot of stress on Titan as a distributed database and prove that it can do the things that we say it can do. What we did is we created a 16 machine cluster on Amazon EC2. These are the high 4x large machines. They're very expensive machines, virtual machines with a lot of memory. I forget the memory, I think it's like 128 megs with 2 terabytes of disk. And so from those 60 machines, we represented a 120 billion edge graph. And the way we constructed that graph is Matthias Brokler, my partner, he constructed the graph, and it was using a lot of cool techniques. For example, discussion boards were text snippets sampled from the Project Gutenberg. Project Gutenberg is a non-copyrighted text, so he would sample snippets of text to make discussions, and then from the text he would use OpenCalais to generate relationships to concepts. OpenCalais is it's in the RDF world, but allows you to map a piece of text to the concepts in that text. It does some kind of NLP to figure out which concepts you're talking about. He needed to create university names, so he had the list of universities for the US. He got that from the Census Bureau data set and was able to do take out university, put community college, take out university, put institute. So he made a whole bunch of fake university names. He took the US Census Bureau's name catalog for all American citizens and flipped names. So Marco Rodriguez, Marco Smith, James Rodriguez, James Smith, and did the cross product of all the names to create enough names. He needed abstracts and course titles, used MIT OpenCourseware and their titles and kind of did manipulations to the title to generate more titles. Intro to Abstract Algebra 1, Abstract Algebra 2, so forth and so on, so that he could create a representation that had nice real world properties to it. So we had a simulation of this graph. And this graph ultimately represented 6 billion edges, or 6 billion vertices and 121 billion edges. And we were able to serve 10,000 transactions a second with return times at 200 milliseconds. So we wanted to make sure that this architecture, machine architecture, could handle that load. And the way we handle that load is, while the Titan graph is represented on these servers, we have 80 less powerful machines, and you can think of those as your web servers that ultimately feed the web application data to the user who's going to be clicking. And those things are just slamming this cluster with queries. A bunch of traversals, gremlin traversals, are just trying to solve little local problems and returning results to the front-end applications. And so what they need to be able to do, ultimately they need to get this to 100 milliseconds. 100 millisecond runtimes is what you need to get into when you do web computing and you're trying to make sure that people are getting things back to their browser so they don't have a psychological effect of it being delayed. You need 100 milliseconds. So there's a lot of work we're doing to make sure that we can, ultimately we want to sustain about 1 billion transactions a day. And we haven't perfectly done that, but there's a way forward to do that. So with Faunus and Titan, and let's just talk Titan, there's Cassandra and H-based Titan representations, and I won't get into that because it just assumes a lot of background knowledge. There's two ways in which Faunus and Titan work together. And again, Titan is your database and Faunus is your analytics engine. And Faunus is streaming of data. Titan is a database. You just get input data. You create a database connection or read and write data. And Faunus is just going to stream your graph. There's two ways in which these things can interact with each other. You can have intra-cluster configuration in which your Hadoop and your database, Cassandra is the backend database, I'm just keep saying Cassandra, but just assume it to be the infrastructure that's storing things on disk for us. And Titan lays out the graph in Cassandra, and then Hadoop is the information, the thing that allows us to stream data off of the Cassandra nodes. What's nice about having a co-located representation of your Faunus and Titan cluster is that the data is processed on the machine where it's located. I don't have to move things over the wire. The problem with this, though, is then you're also hitting CPU problems. So if your cluster is being read and write to by a lot of users in parallel, and you're trying to do analytics with that same CPU, then you have problems. You're going to bring your CPU load down, and then you're not going to be able to serve requests. And what we see most organizations do is they do their cluster like this. As long as I can get my machines co-located with at least in the same rack or racks in the same data center, and I can get a 10 gigabit line between the two clusters, then I can have my Cassandra cluster on one set of machines, my Hadoop cluster on another set of machines, and just start streaming over. What's nice about this, well, the problem with this is you're offloading a lot of data to another cluster, but what's nice about it is that now, once I've offloaded a snapshot representation of that graph into this cluster, I can just start doing repeated analysis. So the data scientists can start doing all the statistics they want to do, all the plots, without interfering with the production cluster. And this is perhaps my favorite aspect of using Faunus and Titan, is this. And it's vertex-centric computing with Gremlin. And this idea is, what if you have a graph, Titan is storing this graph in a cluster for you. And Hadoop, what's nice about Hadoop and what people use Hadoop for too, is that it's an easy way to manage many threads across many machines. So I can write a Hadoop job and I can just say how many threads I want to happen. And if one of those threads dies before the operation finishes, it'll just spawn up a new thread and repeat where that thing kept going off, or where it last fell apart. So it's like a very nice way to just manage as many threads as you want of computation. And so you can leverage this concept in the sense that I can go ahead and put a little Gremlin script into HDFS and just a file, and it's a just think of it as script, like a little program you want to do. I can stream out of Titan. I can tell Titan to don't give me all the edges, only give me the vertex IDs. So what I want to get is a stream of Faunus vertices, but there's not the edges, it's just a long ID. Faunus vertex with long ID. It's just the IDs. I can feed that ID into a Gremlin script. In theory, all these Gremlin scripts are running in parallel with the ID of the vertex. They're making a database connection back into the cluster and doing some kind of manipulation on those vertices. So now you can think of this little piece of code on every vertex in the graph. And so every vertex now has a thread of execution, and it can just do something on the graph, whatever you want that arbitrary computation. There's two ways in which you think of graph computation. You think of graph computation from the objective perspective, and we were talking about this yesterday while we were sitting at Playa, was that people, when you design graph algorithms, you usually think about iterating over all vertices, and for every vertex, do something, go to the next vertex and do something, and then loop again. Another model of doing it is to think of every vertex as its own thread of execution. It has its own program on a while loop. And its communication edges are the edges of the graph, such that it gets messages in, does some kind of analysis of those messages, and puts messages out to the next vertex. So now you can think of every vertex in your graph as a thread of execution that are manipulating messages like a switchboard on a phone. And that model of computation is very nice because there's no objective observer. It's the graph itself maintains the threads of execution, and this model of using Hadoop to spawn the threads and just to pull out the long IDs and execute code on every particular vertex is this kind of is very nice in the sense that you don't have to do this. You write your algorithms in a very different way. Let me see how to explain this. Like, do you guys understand PageRank? You've heard of PageRank? Do you guys know how PageRank works? Let me describe it in 5 sentences. More than 5 sentences. Okay, you have a graph, and I take a marble, and I put that marble on a vertex. Okay, you have a graph, and you have a hash map. A hash map is a something and some value. And I randomly take a marble, and I put it on a vertex, and I say, oh, vertex 1. And I mark on my hash map. Vertex 1, I've seen once. And then that marble needs to take a random walk of any of its adjacent edges, incident edges, adjacent vertices. Goes to here, vertex 3. Okay, vertex 3 I've seen once. Vertex 2. Vertex 2 I've seen once. Vertex 1. Vertex 1 now I've seen 2 times. Vertex 3 now I've seen that 2 times. You let that marble just keep randomly walking on that graph, and you keep incrementing these counters. Ultimately, these counters are constantly increasing. Ultimately, you're going to reach something called a stationary distribution, given some topological features of the graph, such that all the counters are growing in proportion to each other. As this counter grows, this counter is growing. You've reached a stationary state distribution where the probability of that particle being everywhere is now defined by that distribution of counters. So I can just normalize those counters to 1, and that creates a probability distribution over the graph. Vertices that are central are more likely to come, you're going to keep coming back to them. So they're going to have a higher probability. If I sample that graph, where is the marble? It's very probable it's going to be in a very central location based upon that probability distribution. So that's like a notion of centrality, is if I just let a marble just keep running,
it can give you back the in degree number.
More than degree, because it's a recursive definition based on the in degree. However, certain graphs correlate very well. If you take the in degree distribution of a graph, and you take the PageRank vector, they're both vectors, the vector of degrees and the vector of the PageRanks, and you correlate them, they're very correlated. So in degree is a very good measure of, is a good approximate of PageRank. However, it's more than in degree because it's recursively defined in that way. And so how do you do this? How would you represent that marble moving in this vertex-centric computing way? Well, you have a thread of execution and a vertex just sitting there, and then all of a sudden one of his neighbors gives him a marble, and he goes, oh, and he increments a counter, sends a marble off randomly. Marble comes back, oh, increments the counter, sends a marble off. Marble comes in, oh, counter, sends it off. All the vertices are doing that, incrementing their own little local counters. There is no global counter, the counters are distributed across the graph as properties. And then when you let that go for infinity, so to speak, you stop the computation, and at any time you can just sample a vertex. How many times did you see this? Oh, I saw the marble came to me 1,000 times. How about you? It only came to me 100 times. Oh, so you're more central. More paths seem to go through you than through you. So it's like when you design a graph algorithm. Yeah.
So don't you need to divide somehow by the total number of stuff that?
If you want to get a probability distribution, you can sum all the counters. But you
or if you stop it at the same time, but then you need to be sure that they all have the same the possibility of being
Yes. So how many iterations you do? I mean, you have to make sure that you're getting to that stationary distribution. If I only run it twice and I did it there, then of course it's not a cut. So you have to go to quote unquote infinity, and that division number is actually how many times you just let that thing run. Because every step, one counter is being incremented. So I just know how many steps happened. Then whatever counter I get back, I divide by the total amount of steps I took, and that's my probability.
That's what I mean. You divide by the total number.
So you get a probability. But if you're just doing comparative, you can say that this one has those probabilities in large graphs. The floating point values get so tiny, and you can actually get off the floating point range or the double range, because if you have, let's say, 1 billion vertices, what's 1 divided by 1 billion? You're starting to get into 0.00009. You see what I'm saying? And that's assuming an equal distribution. They're going to be completely biased. For some vertices, you're going to be getting off of what you can represent with doubles. So you get into kind of rounding errors and stuff like that with very, very large graphs if you go into probability distributions.
Yeah. So you don't need to normalize to the level of 1, but you can normalize to the level of 1 billion or whatever.
Yeah. So it's like this different way of thinking about graph algorithms, where the sense of you're thinking of what every vertex should do in parallel, versus having some writing a piece of code where you're trying to move a marble and update, move a marble and update, move a marble and update. There's two kind of paradigms in writing graph algorithms, and this kind of model is very attractive in the sense that there's no global coordinator in that. Okay, so presented by me, supported by Los Alamos and the VUB, and this is my partner who is the primary developer behind Titan. Stephen Millett, Paul Jaskovich, Dan LaRoque are all worked with Aurelius and have been helping to design the technology. Aurelius community, Tinkerpop community that develops Gremlin, and Katrina Yim designs all of our logos, and she's very good at bringing life to our software with little pictures. Thank you.
There will be questions now, I guess.
Oh yeah, if you guys have questions.
Can I ask you something?
Yeah, please.
I am surprised, I don't know about Titan, because you're putting everything on Hadoop servers, and as I understand, Hadoop are good when it's, as you say, write once.
Yep.
And not to maintain information and put more information there.
Yes.
So how do you deal with the two together? Or is
So,
Titan?
have you heard of Cassandra or HBase? So Cassandra is developed by Facebook and then made public, made open source. HBase was developed by some of the fellows who created Hadoop, and what it is it's called a big table, a big table clone, big tables, and if you think of a relational database, it's a square, right? So you have rows and then you have columns, and all the columns have to be of equal length. And if you don't have a value for a particular column, you set to null. The semantics of all the columns mean the same thing, and null is you don't have a value for that. In the big table model, you have rows, but then you can have an arbitrary amount of columns, and the columns can be arbitrarily labeled with arbitrary values. So the columns don't need to match between different rows. So I can have rows with only 5 columns and rows with up to 1 billion. I think Cassandra supports 2 billion as a positive integers, the amount of rows it can maintain, or columns it can maintain. So now if you think of that as an adjacency list, a row is a vertex and every column is a new edge. And I can read and write to that data structure. They're optimized not for sequential reads, they're optimized for allowing me to go to a particular row, to a particular element in that row and mutate it, or read it.
So you keep the space for everything, and then you put it there, exactly the place you need it.
Yes, and that's what indexing structures allow us to do. When I stream this structure out using Hadoop, I don't maintain all these indices, because those are for random read writes. And so this is a completely different data structure that's completely serial and not indexed like you would have in a database. Both of the...
How do you do to scale?
To scale what? The database?
Yeah.
What's nice about it is now all these rows just need to be stored on one machine. As long as you can store that one row on one machine, you can scale it. Because I'm just, one communication can say, for this particular vertex, add an edge. For this particular vertex, remove an edge. For this particular vertex, what's the adjacent vertex, and then go get that vertex.
Yeah, but you have already the index in the plot that defines where it is.
On this side?
Yeah.
How do you scale the index?
That's a very good question. Yeah. So, okay, it's a little bit more complicated than that. So what you have is actually, you have a hash.
Yes.
You have a hash function that's going to tell you on which machine the particular row of the adjacency list is, the key is, and then a hash to find where it is on the disk. These indices right here are local indices to the row. You can't say, you cannot say in these kind of systems, like you can do in relational databases, all people named Marko. You can. You can because you make, let's just assume, there's ways, tricks to get around it, but the theory is to say you can't ask global questions of these kind of data structures. In theory, you can't know how many rows you have. You can't make when you get a distributed environment where you have multiple machines and data distributed everywhere, to ask a global question is a scam, in essence, unless you have some kind of indexing structure. And so those are no-nos in these types of databases. In a streaming database, in a streaming framework, that works. These little data structures right here, these are local to the particular row, and the way we use those for graph processing is we call them vertex-centric indices. If I have a vertex and I need to know all of his friends, then I can go to his friends and then I can jump to that in the row and get all the friends. Or if I need to know all his familial relationships, I can jump to the family relationships. I don't need to linearly scan and say, is this a friendship edge? No. Is this a friendship edge? No. Is this a friend? Yeah, that one. No. Why that is good is if you're dealing with graphs on the small, 100 edges, 200 edges, a linear scan is fast. In fact, it's probably faster than doing a hash lookup in a set. Just doing a linear scan, there's less data you're dealing with. If you're dealing with a vertex, there's a certain point at which an array list is faster than a hash set. So at a small scale. Okay, so now at big data, when you start to talk about lots of vertices with many edges, linear scans start to break down. And what happens is, at scales of a billion edges of the whole graph, you're going to have a lot of vertices that have 1 million edges. And 1 million edges, now you need to start thinking about a vertex like a relational database table. If I had 1 million rows in a relational database table, a linear scan is going to kill me. So I build an index into that relational table so I can just jump arbitrarily. So now think of a vertex like a little table. And I need to build indices so I can jump to friendship relationships made in the last 2 days. Friendship relationships made in the last... products that I've rated high, greater than 5. Now those become little local indices on this table. So now you start thinking of, wow, this actually is a pretty big data structure we're dealing with. And so that's how you have these kind of localized indices to do, to arbitrarily jump to edges in that graph. And this gets you around the supernode. One of the problems with graph processing, if you go to graph processing frameworks, is you're always going to hit that supernode. You say, well, there's not many supernodes. I mean, there's only a few Obamas, a few Britney Spearses. But if I randomly take a walk, they're gonna keep showing up, given the probability distribution of that marble. So I don't care if there's few of them. They seem to exist on every path. I keep running into them. So one of the tricks you can do is to say, instead of fighting the supernode, what I'll do is I'll build indices. And most of the time, what I'll say is, when I get to Obama, I don't care about how many people follow him. I might care about the last 5 political relationships he made. And now that's a jump to political relationships in a sort order on time, and I can grab the first 5 on that sort order. So now Obama is not a supernode. He doesn't look big because I have indexing structures that let me jump into it. And you
How do you know that you will be interested in the last ones and not in, for example, all those that are from Alabama or all those that are...
So you have to be smart when you design your indices, and this is where you design your indices for the queries you want to do. And so you have to say, like, I care about time is going to be very important. If I'm doing like friendships, I want to know recent times. Or products, I don't really care all the things you've clicked on, but I care about the things you've rated highly. So I want to sort on ratings. So 5s and 4s and 3s and 2s and 1s, so that it's very fast to get the highly rated things for recommendation, let's say. So
you mean that you have some kind of a categorization that tells you which are the important distinctions?
Oh, most definitely. I mean, you design the database schema. You have to a priori know the data you're going to put in there.
It's very dynamic. You create it for a purpose and then you're thinking
So you can
But you need to select this only for the supernodes, or do they apply it to all the nodes?
So Cassandra is very nice, and this is why I got to the linear scan versus when does a linear scan become slower than an index? If I only have 10 elements, a linear scan is going to be a lot faster than building this B-tree structure into those 10 elements. And so it's a waste of resources. Cassandra says, once I get a certain, you can set a property, say once I get a past a certain byte, the size of the byte table, it builds the B-tree for you. So when it is a linear scan, it is no longer efficient. And so, and there's another thing you can do with...
and that becomes interesting because you have a powerful distribution, which means that there are a few supernodes and most of them are ordinary nodes, so it can be very differentiated in how you treat those nodes.
Exactly, exactly. And so most of your rows, not most, but lots of your rows are not going to have these little indices in them because it's just very fast. There's 2, 3, 4 edges. And in Cassandra terms, it's how many columns you have. If I have a billion columns, build indices. If I have 3 columns, don't build them. So if you're you seem you're computer science in some sense, you're a database, are you a professor?
No.
Oh.
No. I'm a little bit in big data, but just reading about it.
Okay.
And I was in machine learning.
Okay. So Cassandra is very cool. Look into cassandra.apache.org, and then what types in. So the fellow who wrote probability similarity logic, it's Liane Gatour, you know, that lady from machine learning. So his advisor was her, and they've been doing a lot of probability similar logic, and that's why he got into graphs. But he went into the way of databases and data structures and whatnot. So, but we kind of have a bent on using graphs for optimal machine learning. But yeah, Cassandra is a pretty wild piece of technology. It's very cool.
I'm not sure that I know how to ask the question that I want to ask. In your description, there still is this distinction between the data which is represented and the means of computations. And these are mediated by some protocol, the Hadoop, if I understand correctly. Now I'm trying to think about the future of it. Just could we have, for example, to represent the internet at the first stage, like a graph, where this graph represents all the computational resources and all the memory resources distributed over the net.
Yeah.
And then, if we could create a graph of everything, yes, because I see that this structure that you started your talk with actually can represent anything. So we can represent all relations between everything and everything.
Yep.
It is dynamic.
Yep.
And we also have, we can have a graph that represents all the computing and memory resources. If we put one upon the other, we get just a graph that computes everything on everything. This will be the global brain, actually. Kind of. Now these protocols are actually a kind of intermediate kind of a technology because we still don't know how to map one into the other. It's something very regular. The Hadoop just take, okay, I have a cluster of machines. They are identical. Each of them can run such and such number of threads or such and such amount of memory. But this is something artificial. It's not really, if we have the technology, we could do much better than this, to use all the computers on the internet.
Oh, yeah. So, there was like SETI at home, you're talking like a SETI at home, but where EC2 is everyone's idle clock cycles? Is that what you mean? You know what SETI at home is?
Yes.
So like SETI at home, but for arbitrary computation.
Yeah, but SETI at home is really using something very regular, but this graph technology allows you not to be very regular about how resources, machines, and data are connected to each other, because you really can create, how did you call it, not the label, the property graphs, that every edge has multiple relations to
Yes.
So I'm just thinking about it. Do you see something like this? How does it go into the future, this kind of technology?
I had a similar question, so maybe let me formulate it as well, and together we can I'm thinking in terms of the semantic web.
Yes.
Eventually, all the knowledge that humanity has will be somewhere, formalized somewhere, but it will not all be on one computer, it will be spread on many different computers, so if you want to ask a question to the semantic web, you will need to have this kind of distributed protocol that's quite efficient and that can jump from one node to another in order to find, by a very long path, perhaps the answer to your question.
Yes.
So are you imagining it in a sense as something that might be a precursor of the semantic web that is really computing and is distributed over all computers?
Yes. So my PhD thesis was this problem. The problem with the semantic web is that everyone's representing these aspects of their graph on their on these computers represented everywhere. And if I want to query the semantic web, I have to dereference a URI. And so I go and grab that URI and get its outgoing edges. And then I go and grab that URI and get its outgoing edges. So I'm constantly querying and pooling data to my local machine in order to do a traversal. The problem is they created linked data. They call linked data is like kind of the new semantic web term called linked data because it's not necessarily tied to semantics. Though the logicians got into the RDF framework early on and put all this ontology stuff and made it semantic, quote unquote, but it's failing because of runtimes and whatnot. So linked data is the new term. And the problem is linked data didn't come with a linked process. So they came with a way to represent a distributed database, but they didn't come up with a way to do a distributed computation on the database. And some of my PhD work was on figuring out how to make a protocol such that when I do a traverser, I propagate the code for that traverser to the machine. He runs, and as he needs to jump, he jumps between the machines, and it comes back home with the results of the computation. And that's something it's like fallacies, and it's like half-done infrastructure. Well, it depends on what you're trying to accomplish. It's like, what we were talking earlier, when they created the internet, they created a way of distributing information, but not a way of distributing money or value or economics. So we don't have a nice way in which we expect everything to be free on the internet because we don't have a way of disseminating money easily on the internet. And so it's like when you build a protocol, you got to say, okay, well, this is a distributed graph representation, but how am I going to process this thing? And that's why it's semantic web, because they didn't provide that next step. So if you're going to provide a way for people to, like the internet, if you're going to provide people a forum to create things and allow other people see your things, you need to provide the incentive and the money-making infrastructure such that when things get saw, you get money for them. And we just never did that. So it's just like this half-done protocols in my view. There's a lot more. There's more to it that we just wasn't accomplished.
But so you mean that what the semantic web, it has the data structure, but it doesn't have the distributed process.
No.
And this may be a way towards that.
So this starts from the notion of your own particular cluster, and yes, you can grow a cluster on that, and we do routing, gremlin routing between the machines to solve a particular computation. Yes, you can just keep adding Cassandra nodes. What's really nice about Cassandra, and you might pick up on this, is it's not a master-slave model, it's a master-master model. So I can start up a Cassandra node, and then it just needs to have a seed vertex. It needs to know about one other IP address that is a Cassandra node, and then it joins what we call the token ring. And so let me explain how this works. It's pretty crazy. So you have these long IDs which represent these keys, and these keys are 128 bits in Cassandra. And so if I have one Cassandra node, that Cassandra node is going to hold 0 to 2 to the 128. Any key in there. If I have two Cassandra nodes, I make a 50-50 split. This one owns to 164, and this one owns to 64 to 128. I can do, just think of it like a pizza slice. If I add more nodes, I can have other nodes that do replication. So I have one node that represents this part of the pizza slice, another node that overlaps and represents some of this pizza slice, such that I can make sure if one node goes down, that other nodes are able to still serve the data, so I replicate data. I can have so many nodes and say, you know what, I have 3 times replication of my data. And I don't need that. I'm going to start decommissioning nodes such that the slice that they own starts moving over to other machines. I'm going to say, I'm going to have, it's coming Christmas and my store is going to be hit a lot by people purchasing stuff. I'm just going to spawn a bunch of Cassandra nodes. They're going to join the ring and start taking slices of the token, and the data automatically moves over. It's called elastic scalability. It's this notion of decommissioning and commissioning nodes and having data automatically propagate to make sure you keep that distributed representation and maintaining replication factor. So replication factor is very important because when you have a lot of machines just die, disks just die. So you got to make sure you have the probability of losing data is very low due to replication. So Cassandra is a fascinating piece of technology in that respect. It has that kind of ability in the sense where Pierre could start up a Cassandra node and join my ring, and then he can start getting some of the data. He can maybe take, because it's a laptop, just take a little tiny slice of that 128-bit ring, and so he owns just a little piece of that data, so forth and so on. So everyone can own just a little piece of that 128-bit address space. 128 address space is not going to represent all the world's information. It's not like a U or I, which is infinite.
What is the size, the maximum size of the cluster in number of...
Twitter runs a so Pavel Jaskovich runs a 400 node Twitter cluster at Twitter.
Really?
400 nodes, 400 machines.
Yeah. So it's not...
Oh, yeah. Well, yeah. So, yeah, you got to start thinking, too. I don't know what so people haven't done it like that, where everyone has a little Cassandra instance and we split this token ring up. The largest cluster I know of is Twitter, which has 400 machines on it.
Still, orders of magnitude too small, but yeah.
But I don't know what the I would have to look. But I don't know what the theoretical limit is. Can you just keep adding IP addresses? I don't offhand. I don't see why that would be a problem. The problem though is when you this is the problem. If I have data and then you join my cluster, I got to, and you're in Belgium and I'm in New Mexico, and you want to take 50% of my data, now I got to export 50% of my data to you. When people join this now, let's just, that's fine for, we do a one-time cost of that 50%. The next person that joins and is going to take some of your data, hopefully he's maybe in France or in Germany and he's only going to take a certain slice of your data and he doesn't need to communicate back from me. You start to get into regional topologies that need to be accounted for and how you start partitioning data. And I don't know, you have to be smart about how machines come online and which part of the token ring they grab, such that the token ring they grab is regionally located relative to the person they're grabbing it from.
You mean regionally in order to minimize the time to...
Yes. But in principle, I don't see what off the hand. And I bet you can make some kind of mapping between your IP address, the IP address coming in, and which part of the token ring they join. Because there's IP addresses are correlated to space. So in theory, it's possible, I would say. Yeah, but this is, it's crazy. It's a very well designed piece of technology. It's not my technology, this is something else. So I'm not just...
Well, I'm a little bit interested in the implementation issues and more in the conceptual issues of graph computing in the sense of traversals as a kind of a general paradigm to represent any kind of computation.
Yeah.
Indeed, that's also why I mentioned semantic web. You think of the semantic web as kind of a distributed graph-like representation of all of humanity's knowledge, and then you can ask very complicated questions that require the combination of data from very different parts. If you have a smart traverser, you can do that.
Your biggest problem is not going to be the smart traverser. I think that's the easier problem. The biggest problem is going to be data disambiguation and data cleansing and data loading. Yeah, there's one of the problems with the semantic web is it's assuming a priori knowledge of the ontology. Yeah. Marko works for, I live at.
I know. That is the real big problem.
Yeah.
And that is why the global web design is first at the kind of a lower level, like a neural network or an associative network where things are not as clean.
Yeah.
You work more kind of associatively and saying, you may be looking for this one. This is the answer to your question, but you may be interested in this.
But ultimately, those things need to derive labels, and that's like the huge problem, going from signal to symbol. When I have a signal of just noise of information, and I need to be able to label that information. If I do have, like the nodal growth stuff you speak about, if I'm impinging information on this graph and it's potentially growing new nodes in order to encompass or to represent that patterns in that information structure, there's no label on that to say that represents Francis Haley. So it's like this notion of how do you go from signals to the labeling of the structure, so that you actually have like your labels also have to be nodes themselves, that then somehow get joined, so that the Francis Haylagen node that has been grown and the word Francis that has been grown, now there's a link between the Francis and that node. I mean, there's like this, because it's hard to query something if it doesn't have any labels, because ultimately the human is consuming.
Well, you could extract labels by, for example, having lots of textual descriptions and then kind of extracting the most common combinations of labels, things like clustering or related semantic analysis. There are ways of extracting it to what we green labels, but this would be able to find labels.
Also, this ambiguation is never perfect also for humans. So we disambiguate knowledge and information depending on the context, the immediate context of something that we want to know or to do. And it's never perfect, but it works. So it doesn't have to work. It doesn't have to be perfect, like we think in computer science that you need to have the graph with all the relations, etc., in order for it to work. No, it can be quite dirty and still be very effective for many applications. More than we tend to believe, actually.
Well, yeah, that's my general spreading activation paradigm. Activate all the things that are relevant relative to how relevant they are, and then hopefully they will allow you to say this is the more likely outcome than this one. It's the whole of all the little things that accumulate in a particular pattern. In this context, that's probably the solution. And if the difference between the different contexts is big enough, like this thing that you do also the IQ it had to choose, it had 4 possible answers, it had to choose the most likely one. It wasn't always correct, but it was good enough that it could solve a number of seemingly intelligent questions.
So I have the question related to the context, to this kind of. So the link between two vertices is defined by the sort of whether there is a link or whether there's no link, defined by contexts of these two vertices. Can you calculate, sort of compare contexts with all this stuff?
One of the companies we're working with, they have this notion of I talked about this yesterday. They'll have like Obama from text, Mr. President, President of the United States, Barack, Michelle's husband, and then these are all nodes from text. And then what they say is they need to figure out that actually these all nodes represent the same thing because this node touches the White House, this node touches the White House, this node touches the U.S., which touches the White House, and so they're all seem to be linking to the same thing. So I'm just going to group all these together and make a new node that's platonically representative of Barack Obama. But then it's platonically representative of Barack Obama within the political representation. Michelle Obama might have fun in Cabo San Lucas, beautiful dates, walking on the beach, man, and then that's Barack Obama. And so that's Barack Obama platonically from the concept of his wife's perspective. So it's like this notion, this problem that we have in external representations of information that we all share collectively is because my concept of Francis is completely different than Victor. When I say Francis, that spawns a whole Belgium and GBI and Europe and things like that. And where for Victor, he's already in Europe, so Europe isn't a node for him because he's embedded in that context. So it's like there's this a completely different emotional response or conceptual response that I get when I think of Francis than when you think of Francis. And if we're both going to share the same data structure and say Francis, how do we start to say, well, no, that's your interpretation of Francis, my interpretation of Francis, or is it just going to be Francis, which is, what is Francis? I mean, I'm saying like Francis is my interpretation and that's a Francis interpretation, and we don't seem to model knowledge like that.
That's some kind of a closure operation. This kind of a closure operation kind of takes a boundary and says, this is the essence of Francis, all the rest are local associations that maybe are not so sharp. You need something like that.
But what is the global representation? Would you say is it like a professor? If Francis is a professor at the VUB, is that the kind of like the shared global?
No, I mean I should have an identity as a person. The handy thing about persons is that they have an identity. It would be much more difficult if I would speak about, for example, a particular plant that goes in my garden.
Yeah.
It goes there now, but maybe next year it is split in two, or maybe it has died, or maybe it has gone so much that I don't recognize it anymore. With people, it's pretty easy to say it's the same person.
Yeah.
So that's why ontologists work for people. They work for things like names, addresses, it becomes already more difficult if it's about professions, because you may consider yourself to be a plumber, but somebody else may not consider yourself to be a plumber. Some things are easy to put in a hard category, some things are fuzzy, some things are completely difficult. It's like, Francis is a nice guy, yeah, but the category of nice guys is very fuzzy and very subjective. The category of professors, that's already much more well defined. The category of 52 years old, that's very neat.
Yeah.
Yes, subjective categories will need a different theory.
Yeah, it's the global data structure seems kind of odd to me. It seems like you have local data structures and some communication of my representation of Francis to Clement's representation of Francis that intermingle. It's like everyone has their own individual database, and those are the boundaries of knowledge. It's not a single knowledge substrate. Much like you bound agents. Why do you bound an agent? Because they have an interpretation of the world. You wouldn't need agents if it's just all one knowledge structure. That would be your agent at that level.
Just a question which is somehow connected. You mentioned before a huge graph that you processed with 100 billion
edges.
Edges, something like this. And I wonder how many properties characterize one edge or one vertex in such.
I have the distribution. I think on average, like there's like 3 or 4 properties per.
3 or 4 properties.
Yeah.
So the number of edges and the number of vertices are vastly more than.
Yeah. And to the point, edges is your biggest number. So when you scaling factor, your edges are going to blow up everything else.
Suppose now that we will have a very dense kind of graph, so many properties, because if we will build the semantic network of all our knowledge, I can assume that every edge will have really many properties. So would this kind of processing will be still efficient for something like this, where every edge will be in itself a kind of a database with a lot of information?
Yeah, well, why would edges have properties? Give me some examples of why would an edge in a very large knowledge structure have
all my
properties?
Connections, all the something that represents me, all my connections.
Those are vertices.
Yes.
The principle is that you try to represent properties as edge and vertices. So the edge and properties.
Are you mixing up the word edge and vertex?
No, I think if you say you have the property of being 53 years old, so that means there is a vertex from 53 to you with the label age.
No, it's understood. One of the powers is that you can
put properties onto a vertex or an edge.
On a vertex or an edge.
Yes.
Interesting on an edge. You can overload it with a lot of properties, and then actually you represent in parallel many graphs. So you can. It's not one graph, because you can choose one property, and then you cut everything you have according to this property, and you get a graph representing only this property. And then you can do it on triplets of properties, and so on and so forth.
So what you're saying is a vertex relates to another vertex, and there's a label on that edge.
Yes.
And you have different labels, and therefore you have different intersecting graphs. Same vertex sets, multiple edge sets. But then within an edge set, Marko worked for, and then you have timestamps on that. So then you have work for time. So you have time slices. It's another representation of a graph within that representation. There's no efficient. I don't know why you'd have many properties. It's because I would like to know an example of when you would have a lot of properties on an edge.
Think about
you have a time, a rating.
I'm just thinking about things that are very hyper-connected to each other. So
those would be
connections
to a vertex. They wouldn't be edges. Wouldn't have those properties.
So maybe it's not relevant. I don't know. So usually you assume that there will be quite limited number of properties per object.
10 is starting to get a little egregious.
Okay.
Yeah. And on an edge, you maybe see 3 or 4, like a timestamp, maybe like some kind of a permission, like whether you read or wrote, read or write, or has been validated by a human, a true false. You don't really see many properties on edges, at least in practice.
I see. Okay, that answers my question. I need to think about what it means.
Okay. Anything else? Cool. Thank you, guys.